I am Munot and welcome to the School of Physics, and today we are going to start with heat related chapters. So today we are going to start with heat, wow what a pen, heat transfer. Okay, today we are going to start with heat transfer. Now what is heat transfer? Heat transfer is heat getting from one body to another. So the first formula that we are going to see is the scale, the temperature scale. Okay, so the temperature scale goes something like this, that temperature in degree Celsius minus 0, that is the lower limit, is equal to upper limit minus the lower limit, is equal to temperature in Kelvin minus 273 lower limit upon 373 upper limit minus lower limit 273 is equal to temperature in Fahrenheit. Temperature in Fahrenheit minus the lower limit, that is 32, upon the upper limit 212 minus 32. So here, if direct questions will be given in which you will be asked to convert the temperature in degree Celsius to Kelvin or Fahrenheit. So this is a very simple and very commonly asked question. Okay. Then the next thing that we are going to do is see the normal equations. PV is equal to nRT, that we'll see in kinetic theory of gases. PV is equal to nRT. Okay. Now I'll talk about conduction. That is sorry, not the conduction. First we'll cover expansion. Okay. So what happens is, suppose, now listen very carefully. Suppose we have a rod of length L0. Okay. I heat this rod and it becomes of length L. I heat this rod and it becomes of length L. Then we have to find what is L. So L is given by a very simple formula. L is equal to L0 1 plus alpha delta T. So I have heated it from T1 to T2. So the delta T will be, delta T is equal to T2 minus T1. Okay. So that is delta T. So linear expansion is equals to initial length L0 1 plus linear expansion coefficient alpha delta T. Now when we go to do this with volume, area. So what is the areal expansion? We just have to do a small change. We'll write it down as A0 1 plus 2 alpha delta T. Okay, this is areal expansion. Rather than alpha, we use 2 alpha, which 2 alpha becomes the areal expansion coefficient. Similarly for volume, we write it as V is equal to V0 1 plus 3 alpha, that is the volumetric expansion coefficient delta T. So we have to just remember all these three formulas. This is our expansion. Now I talk about conduction. So conduction is very simple. Conduction is, you remember the formula in current electricity that you have studied in class 9th and 10th, right? So we remember that formula, conduction, it is V is equal to IR. So there we had V is equal to voltage, right? V is equal to voltage there. Here we'll have, instead of voltage V2 minus V1, we'll have T2 minus T1. T2 minus T1. Okay. Then there we had DI by current, that is dq by dt was current. dq by dt was current. So here we have heat, dq by dt, that is the amount of heat transferred per unit time as our current in this formula. Okay. And there we used to have a resistance, right? Resistance R. Here we have thermal resistance, and thermal resistance is called as, here we have thermal resistance, and thermal resistance is L by Ka. Now I am telling you what are the meanings of this formula. So suppose I have these two rods. Okay, you remember parallel and series. So I have these two rods. Okay, so this area of cross section is area A. This length is length L. So rather than connecting it with series, first we do it like this. This length is L and this is like the T1 and T2. Okay, from temperature 1 to temperature T2. Okay, So what is the amount of heat that has transferred per unit time is dq by dt. Okay, L is done. K is the thermal coefficient. K is the thermal coefficient. So L by Ka, here thermal resistance is L by Ka. dq by dt is done. Instead of voltage we are using temperature. So what is the amount of heat transferred per unit time when the heat transfers from a rod of cross section area A from temperature T1 to T2, and the thermal length of the rod is L and the thermal coefficient of the rod is K. Okay, so now we'll come to combinations that we saw in current electricity. Similar combinations we'll see here, that is parallel and in series. Okay, so we'll see the combinations now. Okay, so here we have, so just with the concept of resistance in thermal electricity we can also derive the combinations here. So here we have two rods in series, right? Two rods in series, like there we had two resistors in combination in series, R1 R2. So what used to be the R net there? The R net there used to be R1 plus R2. Similarly, what will be the thermal resistance net here? It is R net, thermal resistance net, is equal to R1 plus R2, that is L1 by K1A. Since area of cross section in both of these are common, so we write A for both plus L2 by K2A. Okay, so this becomes 1 by A, L1 by K1. So this is L1, this has K1, this is A, this is L2, this has K2, this is A. Okay, so L1 by K1 plus L2 by K2. So this becomes the R net for this combination. This becomes the thermal resistance net for this combination in series. Okay. Now let us see the combination in parallel. So what will become of parallel? So in parallel we will have something like this. In parallel we'll have something like this. So here area might be different. This might be A1, this might be A2. Okay, this is L. L in both the cases is same. Okay, so since we remember 1 by R parallel in current electricity is equal to 1 by R1 plus 1 by R2. So R is equal to L by Ka. Okay, so 1 by R1 will become Ka by L. Since L is common for both K1 A1, so this has K1, this has K2. So K1 A1 plus K2 A2 upon L. Okay, so this is 1 by R parallel. Now reciprocated, so you will get R parallel is equal to L upon K1 A1 plus K2 A2. As simple as that. So here is the thermal resistance in parallel, L upon K1 A1 plus K2 A2. Okay, all right. So the next thing that we shall see is going to be the simple laws on heat. Okay, this is very important. These are like 4 laws. The first law that I am going to tell is about the Kirchhoff's law. So suppose you have a body, right? Suppose you have a body. Say this is the body, and you give it 10 joule of energy. 10 joule of energy comes, 10 joule of energy is received. Suppose it absorbs 6 joule of energy, and it radiates 4 joule of energy. Okay, then there is this constant called absorptive power. Absorptive power is called as the energy that is absorbed upon the energy that is received. So here the absorptive power is 0.6. Then there is also another thing called emissive power. Emissive power is the energy radiated. Here it is 4 joule per unit area, per unit time, per unit solid angle. we will not go into details. If it won't come into that detail. What will come is actually the law. So the law is, what the law says, that E upon A for any body, E upon A is equal to emissivity of a black body, which is equals to 1. So this is our law number 1, which is Kirchhoff's law. Okay, now we see the next law. The next law is Stefan Boltzmann's law. So what it says is the energy radiated per unit time, dq by dt, energy radiated per unit time by any body is equals to EA sigma T की power 4. That is directly proportional to absolute temperature की power 4, where E is the emissivity, A is the area. What is important is this thing. What is important is this thing, sigma. So we have to remember the value of sigma. Value of sigma is 5.67 into 10 to the power minus 8. I call it as 5678 formula. So 5.67 into 10 to the power minus 8 watt per meter square Kelvin की power 4. Okay, so energy radiated at any time is directly proportional to absolute temperature की power 4, and the constants are EA sigma, where E is the emissivity, A is the area, and sigma is the Stefan Boltzmann constant, which we have to remember the value 5.67 into 10 to the power minus 8. Direct question on formula will come. Okay, now the third law is so we have seen, now we will see Wien's displacement law. We will see Wien's displacement law. Okay, so Wien's displacement law says that when the energy is radiated, the energy, the lambda, the wavelet corresponding to the maximum energy radiated at its absolute temperature, okay, say this is lambda m. So the maximum radiated energy is here, lambda at this position of lambda m. So lambda m into the absolute temperature is equals to B, where B is Wien's displacement constant, and we have to remember the value of B is equal to 2.88 into 10 to the power minus 3, 2.88 into 10 to the power minus 3 meter Kelvin. Okay, so this is what is to be remembered, the value of B. The direct question will come on the exam. Energy, the wavelength corresponding to the maximum energy radiated into its absolute temperature is equal to this Wien's displacement constant. So this, which is B, which is 2.88 into 10 to the power minus 3 meter Kelvin. Okay, now we come to Newton's law of cooling. Okay, so this is the last formula of the whole chapter. So what is Newton's law of cooling? Suppose I have a body cooling from temperature T1 to T2. Okay, T1 to T2 cooling body. Okay, and the temperature of surrounding is Ts. Okay, now we know what is K, we know what is S. K is the constant, K for Newton's cooling constant, and M is the mass, and S, so K by ms is the thing that we have to remember. M is the mass and S is the specific heat. Now the formula says that the cooling T1 to T2 in time t is equals to K by ms. We have to remember this formula. Direct application of this formula will come T1 by T2 by 2 minus Ts. This is Newton's law of cooling. Or in terms of differentiation and integration, if we have to write, we'll write it in terms of calculus. It is dt by dt, that is change in temperature upon change in time, is equal to K by ms. The value of K, M and S will be given, is equal to will be equal to K by ms T minus Ts. Okay, dt by dt is equal to K by ms T minus temperature of surrounding. This is for any absolute value, and this is for temperature T1 to T2 cooling. So this is Newton's law of cooling. This is Newton's law of cooling. Newton's law of cooling. So guys, this was our chapter on heat transfer. Very important formulas. You just have to know the meaning of the formulas, remember the constants, and apply them directly in the final exam. So very simple chapter. I hope you enjoyed this lecture, and please subscribe to my channel.